of paramagnetism into a loop known as hysteresis loop, which we'll revisit just in a moment. Which, in the ferromagnetism, even at a zero field, you could still have a remaining magnetization. Okay? So the material could somehow be magnetized on its own. Okay? The reason of which will become clear just in a moment. Okay? So in nature, diamagnetism universally exists in all materials. Whenever there's a moment, there's a diamagnetism in one way or another. However, despite of the universality of diamagnetism, the typical value of diamagnetic susceptibility, or the slope of this negative curve, is much smaller than the slope around zero field for paramagnetism. So in most materials, I'm not saying all materials, but in most materials, the paramagnetism dominates the diamagnetism. Okay? But I mean, whenever there's a rule, there's an exception. So I'm not going to talk about the exception, but for typical cases, the diamagnetism has a much lower, smaller value than the paramagnetic susceptibility. All right. So this is just a phenomenological picture of what is magnetic susceptibility. Then how can we quantify paramagnetic susceptibility? Now this calls for some mathematics. So why not let's just start with the simplest case, where only the spin 1/2 is considered. No orbitals, simply a spin, the simplest case. So in this case, if we consider an ensemble of spin 1/2s, and all of those spins are mutually independent. So each individual spin could react to the field individually, regardless of its neighbors. Okay, so this is a simplification. So when there's no magnetic field, then the spins, under thermal agitations, will be randomly oriented. But once you apply a field in one direction, then those spins, have a preferable choices because of the Z-man field. So for the spin up, then it has a lower Z-man energy. Well, for the spin down, it has an Z-man energy penalty. Okay, because the spin could only take up and down. So the partition function for an individual spin has two terms. Okay, and it ends up with a cosine function. And the argument of cosine is the ratio between the field and the temperature. Then the free energy of the total system is simply the partition function, log the partition function times the kBt times the volume density of spins. Okay, so this is the effective free energy of a group of independent spin 1/2s. Okay, then with the free energy, we in principle knows everything about the system. So the magnetization is simply the free energy density. The derivative of that free energy density with respect to the field. And this is, this is how the magnetization, it goes as a function of the applied magnetic field at a certain temperature. And the front coefficient is the maximum possible value that M could practically take, because the tangent function will eventually saturate. So this simply reproduces the phenomenological definition on the previous slides. So there's an analytical expression for the curve is simply a tangent function. Okay, the tangent function. And the slope around the zero field, or the linear response region, could be extracted by a direct Taylor expansion of the tangent function. So this slope is known as the Curie susceptibility. And this, the way that the slope depends on temperature is known as Curie's law of a paramagnetic susceptibility. Okay. Once again, the slope in the small field region decreases inversely as 1 over temperature. And this curve is known as Curie's law. So this is the way that we quantify the magnetic susceptibility. Now, with this picture in mind, then we are ready to proceed with more complicated cases where not only the spin, but also could, the orbitals were, in terms of both. So for, still a group of independent magnetic particles, each carrying a total angular momentum J, and J could be very large. It could be like, for example, 7.5, okay, including the orbital and the spins. Then, in the summation of the partition function, we simply involve more terms. It's not simply, exponential x plus exponential minus x as a cosine, but now we involve more terms. But still, we can do this analytically for an arbitrary large angular momentum. So the result is somehow similar to the case of 1/2. For the 1/2, we simply have a tangent. Okay? You have a slope, the Curie's law here, and a saturation. But for the spin more than 1/2, and all the way comes to the infinity, you always have a pretty similar curve, the NB curve, with a slope around 0 and a saturation value for a large field. Now, instead of tangent, now we have a new function out of this multi-term summation, which is known as the Brillouin function. And here, J represents the total quantum number for the angular momentum. Okay, so the Brillouin function reduces to the tangent function in the spin, in the spin 1/2 limit. But it has an opposite limit when the J's practically goes to infinity, and this is known as Langevin function. In the Langevin limit, the choices of the quantum angular momentum effectively approaches a quasi-continuous distribution. So if you still remember the case that we demonstrated for L equal to 2, you have only 5 choices for the projection. But now for the J goes to, for example, 1,000,000. Then you have a lot of different choices, making the choices practically quasi-continuous. So sometimes this is also called the classical limit, even though we know that classically there should be no magnetic phenomena. Okay. Once again, quantum limit for spin 1/2 and the quasi-continuous limit. Everything is included by a universal Brillouin function. Okay. And similar to the previous case, we could directly extract the slope around the zero field, the small field. And this is the generalized Curie's law for arbitrary angular momentum, and is inversely proportional to the temperature. The difference only lies in the proportionality constant. For different angular momentum, you simply have different C's. But the Curie's law is universal. Okay. So, with this slope around the zero field, we could, classify the materials, into different classes. You have a negative value slope grouped into the diamagnetic class, and the positive slope grouped into the paramagnetic classes. But even within the paramagnetic class, we have a really wide range of values for the slope. They could be orders of magnitude difference. And the maximum took place in the transition metal, in the 3D metals, in the iron, cobalt, and nickel. So if you can properly make the optimal alloy out of these transition metals, you could create a material known as the permalloy. Here the perm refers to extremely softy or susceptible, meaning that the material is very easy to polarize by applying a magnetic field. So this is called the permalloy. Okay. Any questions so far? Mm-hmm?
So, previously it started about diamagnetism. So why doesn't the diamagnetic case saturate? Because if it's the same, it's the alignment of spins in a material.
That's a really good question. So the diamagnetism is typically associated with the orbital motion. I mean, roughly speaking. And for the orbital motion, it's not just like the spins that you polarize it, but you somehow, I'm just trying to give you a heuristic, but by no means rigorous picture. So the orbital, by applying a field, you could somehow shrink the radius of the orbital motion. And this shrinking could be pushed, at least conceptually, to infinitesimal. So, like I said, this is non-rigorous, but a heuristic understanding. But for the spin, especially for the spin 1/2, you either have up and down. No other choice is possible. Yeah.
So in that case, the diamagnetism is dominated by the orbital.
Yeah. Yeah.
I see.
But there's, like I said, this oversimplified picture. Yeah. Thanks for this is a good question. Yeah. I've been teaching this course for years, but this is the first time I received this question. Any other questions?
Yes, please.
Mm-hmm.
Just I want to ask you about the susceptibility. How can I differentiate between the paramagnetic and ferromagnetic according to this parameter?
For ferromagnetism, it could be magnetized even without the magnetic field. So for example, at a zero field, you could still have a magnetization. So, we will revisit this just in a moment.
Okay.
Yeah.
As I know with the super paramagnetic, it also have the same, more or less, cycle of the paramagnetic.
The shape of the curve could be similar, but the thing is, there is a hysteresis loop, meaning that if you sweep the field back and forth from a negative to positive, then the reaction of the system does not simply reproduce itself on the back and in the forward and backward direction. Rather, it follows a counterclockwise loop. Well, in the paramagnetism, if you sweep the field back and forth, then the system simply follows the same path, just in opposite directions. But here you have a different path in the forward direction from the path of the backward direction.
Okay. And could you have material that at the cycle at room temperature is ferromagnetic and at lower temperature paramagnetic?
I'm sorry?
I mean that we can have or got material that at room temperature is ferromagnetic and at lower temperature paramagnetic.
Oh yeah, that's a good question. So in the next section or two, we will, we will discuss this topic in detail. So yes, there is a finite transition temperature called Curie temperature, above which the material behaves paramagnetically, but below that temperature, the system becomes a ferromagnet, acquiring a finite loop. So yeah, there is a phase transition separating the two phases.
Okay.
We will come to that in a moment.
Okay. Okay. And one question, please. That was one. For example, you told us now that there are first differentiated of the magnetic susceptibility, and there are second differentiated, second derivative.
The second order derivative of the free energy.
When I can use the first and the second.
The first order derivative defines the magnetization.
Yeah.
Well, the second order derivative defines the susceptibility.
Okay.
The susceptibility is this, is the local slope of the curve.
Yeah.
Mm-hmm.
So the first the real part, and the second is the imagination part. You mean that?
You mean the imaginary part of the susceptibility?
Yeah.
That's a good question. So for the static susceptibility, if it has a small imaginary part, it would. Oh, that's a good question. For dynamically, we could. It's more easy to understand. So for dynamical response, characterized by the dynamical susceptibility, the imaginary part refers to the dissipation or damping effect. But I don't think I have enough time today to comment on that. But I will try to come to that point. Yeah. So dynamically, yes. It's easy to acquire a imaginary part besides the real part. representing the dissipation effect. So yeah, I'm not sure if we could go that far today to the ferromagnetic resonance, but if I do, then yes, we will revisit this point. Yeah.
Okay.
Okay.
Thank you.
Thank you. Uh-huh.
So here we are talking about like paramagnetic, ferromagnetic, but if I will take one antiferromagnetic material, then that loop will be just like a paramagnetic material, I guess. Like, then how to differentiate that if it is like antiferromagnetic or paramagnetic kind of thing?
That's a good question. So, I mean, I really hope that I could have another 2 hours talking about antiferromagnetism separately. But unfortunately today we do not have time for antiferro. But the thing is, the short answer is for antiferromagnet, the susceptibility is highly anisotropic. That also highly depends on which direction you apply the magnetic field. For example, you apply the magnetic field perpendicular to the neo vector, then the system behaves more or less like a paramagnet. But if you apply the B field along the neo vector, then the system will still be paramagnet, but it has a much weaker susceptibility. So the susceptibility was highly anisotropic depending on the direction of the applied field. And that is why historically antiferromagnet used to be known as anisotropic paramagnet until Louis Néel gave it a different name, called it antiferromagnet. Okay.
Thank you.
By the way, I think Professor Fukami will talk about antiferromagnet in detail. Yeah. Okay, so let's move on. Unfortunately, the progress is much slower than I initially planned. But okay, so now having talked about the paramagnetism and independent spins, independent particles, now we come to the point of magnetic interactions. So we know that in reality, the spins in the material are never, be independent. Instead, they are strongly coupled. They are strongly interacting with each other. So no spins could freely make its own choice, regardless of its neighbors. So this comes to our next topic, the magnetic interactions, or more specifically, the exchange interactions coupling different spins. So here's an heuristic illustration of 2 neighboring magnetic moments. Their electron clouds have a substantial overlap. So for the electrons, it can move, back and forth between the 2 spins. And then it is the overlapping of the electron wave function that could effectively mediate an interaction between 2 neighboring spins. In other words, the electrons in the overlapping orbit serves as the mediators or messengers among the 2 between the 2 spins, transmitting their information, making them effectively coupled. So this is a general picture. So if the electron clouds of neighboring spins are directly overlapped, then the exchange interaction mediated by the electrons, by the common electron orbit, is known as a direct exchange because they directly overlap. So the direct exchange interaction could be quantified by minimizing the Coulomb's repulsion of the electrons, while at the same time respecting the Pauli's exclusion principle, because the electrons are fermions. Okay? And the direct consequence of this, conditioned minimization is that the wave function must be antisymmetric in order to respect the fermionic statistics. So here, by minimizing the Coulomb's repulsion, then we can first determine the spatial part of the wave function of the electrons, traveling back and forth between 2 neighboring spins. And then Once this is determined, then the spin components will be automatically selected in order to satisfy the anti-symmetry of the total wave function. So practically, you only have two choices: either either the spatial components or the spin components of the wave function for the electrons is anti-symmetric, while the other has to be symmetric in order to guarantee the total wave function to be anti-symmetric. So this is how people quantify the direct exchange. So what is the magic here is, regardless of the microscopic details, all exchange interactions will eventually end up with a universal form known as the Heisenberg form or Heisenberg exchange. The difference on the microscopic is reflected in the Heisenberg parameter, determining the strength of the Heisenberg interaction. So the Heisenberg interaction, by the way, I have to skip all the technical details, just jump into the final answer. So the universal Heisenberg form, well, I call it a universal, but it's not so universal because there's always exceptions. For example, for the couplings of different components, the x, y, z, they could be slightly different. And that gives you a exchange anisotropy, but that is a technical detail. So for the moment, let's assume that, okay, we have an isotropic Heisenberg. And the Heisenberg parameter could either be positive or negative, giving rise to either ferromagnetic or antiferromagnetic coupling, preferring neighboring spins to be either parallel or antiparallel. Okay? So, because the Heisenberg in the direct exchange picture, directly depends on how the electron orbits are, how they overlap. So they will directly depend on the interatomic spacing of atoms, making different elements, ended up with a different sign of the Heisenberg. So that's phenomenologically explains why some materials are antiferromagnetic while some other materials are ferromagnetic. Okay, so this is for the direct exchange. So before moving on, I'd like to briefly comment on another similar interaction is known as the dipole-dipole interaction. Because, at this moment you may think that the dipole field out of one spin could give rise to a preferred direction on the neighboring spin. But the thing is, comparing or benchmark against the exchange interaction, the dipole interaction is 3 orders of magnitude smaller. So it could, so it's hard to practically explain anything. So the message here is the dipolar interaction is always dominated by the exchange interaction, which is orders of magnitude stronger. Okay, so this is for the direct exchange. So where the electron orbits are directly overlapped. But even when the neighboring spins do not have a directly overlapping electron clouds, they could still talk with each other through what is known as indirect exchange interaction. For example, what is illustrated here, this is a transition metal oxide, where the oxygen side provides a p electrons that can indirectly serve as the mediators of the 2 d orbitals, which gives rise to magnetic moments. This is known as the indirect exchange interaction. So, this is the type 1 indirect exchange, known as a super exchange. Okay. So once again, it is indirect because the 2 magnetic atoms do not directly overlap. They overlap through a intermediate atoms, which is a different atom. So this is an indirect coupling. But honestly, I do not see anything super here with the term super exchange, but it is simply known as super exchange. In the super exchange interaction, the sign of the Heisenberg almost always turns out to be antiferromagnetic. It's rarely ferromagnetic. Okay? It's almost always antiferromagnetic. And the material is typically an insulator. Okay? For example, transition metal oxide. Okay? So this is the super exchange. Well, the type 2 indirect exchange, typically takes place in metals. Well, it is still it is still an indirect exchange, but it fundamentally differs from a super exchange because the mediators come from the conduction electrons. So the entire conduction band serve as the mediator. Well, in the super exchange, typically there's no conduction band. It's insulating materials. But for the other type of indirect exchange, and this is known as the RKKY interaction, the mediators refers to the entire conduction band. So this is the indirect exchange in metals. So a defining feature for the RKKY, which also distinguishes from the super exchange, is that the sign of the Heisenberg parameter exhibits a oscillatory feature with respect to the interatomic spacing. So if you slightly compress the crystal or expand it, you could even change the sign of the Heisenberg interaction, turning the material from antiferromagnetic to ferromagnetic per se. So the magnetic interaction for the RKKY mechanism sensitively depends on the interatomic spacing, which also indicates a strong coupling between the lattice vibration and the magnetic oscillation, or magnon-phonon interaction. Okay. So this is for the RKKY. Once again, two types of indirect exchange. The super exchange almost always antiferromagnetic insulating materials, while for the RKKY is metals, and it's not always antiferromagnetic. It's actually could easily turn the sign depending on the atomic spacing. Okay. All right. So having talked about the direct and indirect exchange, now we come to a point to introduce yet another important types of magnetic interactions, known as the anti-symmetric exchange, or Zeroshinsky-Moria interaction. Okay. So the Zeroshinsky-Moria interaction, or simply DMI, exists when the mediating electrons are subject to strong spin-orbit coupling in the presence of inversion symmetry breaking. Okay. Once again, for example, in a super exchange material, the electrons serving as mediators are subject to a strong spin-orbit coupling, and the local environment has a broken immersion symmetry. Then, besides the Heisenberg form, which I claim to be universal, there should also be a different form interaction depending on the cross product of the two spins, while the Heisenberg interaction depends on the dot product. For the Heisenberg, it only prefers either parallel or anti-parallel alignment. While for the DMI, because of the cross product, it prefers a perpendicular alignment on a plane perpendicular orthogonal to the dm vector d. So the dm vector first defines an orthogonal plane, and the spins are preferably be orthogonal within that plane. So you see that energetically the DMI, or anti-symmetric exchange, and the Heisenberg exchange, they have a very different preference. So in real materials, the two mechanisms compete, and the real ground state always results as a compromise between the two parties. Okay, so this is the DMI.
We first decide the D vector or the product of S1 and S2.
I'm sorry?
We first decide the D vector or the product of S1, S2, and the D is defined.
Okay, so I mean, in a real computation, then I think the D vector is first determined. And by minimizing the whole energy, including all participating terms, then you are able to determine the relative orientation of the spins. So the D vector should be determined first. Okay. And the way to determine the D vector could be very complicated in real materials. But in an empirical rule, I mean, we do not have the time to go into too much detail, but an empirical rule is, once the super exchange center is displaced in one direction, then you are making a finite angle between the atomic bonds. So empirically, the dm vector is pointing to the cross product of the twisted atomic bond, which in this case is pointing out of the board or into the board. Okay? So similar things happens when it is the mirror symmetry that is broken. For example, on the interface of a material. So on the interface of a material, because of the different crystal environment above and beneath the interface, the super exchange centers located on the interface could be deflected a little bit, creating a finite angle of the atomic bond. So in this case, the D vector is induced in a direction that is perpendicular to both the plane normal and the atomic bonds. Okay, those are similar. So in the second mechanism, I mean, this could happen even for a material without the DMI on itself. But if you place the material, if you artificially create an interface, you could manually induce a DM interaction on the interface, even though in the bulk material, the material itself does not carry any DMI. Okay. And I'd like to give you another interesting example, which nowadays caught a lot of attention in two-dimensional magnets. So this is a hexagon plane of a magnetic material. It's a two-dimensional magnet. So in this honeycomb plane, for the nearest neighbors,